Hello students, let's begin with a little puzzle. Imagine you are given a bag of Lego blocks, all identical in number and color. If you put them together in different shapes, you get different models, right? That is exactly what chemists discovered about molecules. The same atoms can join in different ways to make totally different substances. This phenomenon is called isomerism. Isomerism is when compounds have the same molecular formula but differ either in the way atoms are connected or in the way they are arranged in space. For example, the formula C4H10 can represent N-butane, which is a straight chain, or isobutane, which is branched, and their properties are not the same at all. Broadly, isomerism is classified into two families: structural isomerism, where bonding patterns change, and stereoisomerism, where the bonding is the same but spatial orientation differs. So, same ingredients but different recipes, that's the magic of isomerism. Now let's talk about the first family, structural isomerism. Here, compounds share the same molecular formula but differ in connectivity of atoms. Think of it as rearranging the seats in a classroom. The students are the same, but their positions change the whole vibe. Structural isomerism comes in four main types: chain isomerism, position isomerism, functional group isomerism, and metamerism. Each type gives compounds very different properties like boiling points, polarity, or reactivity. For example, the formula C5H12 does not give you one compound, but three: N-pentane, isopentane, and neopentane. Each one has the same number of carbons and hydrogens but arranged differently. As you can see in the flowchart on screen, structural isomerism is all about connectivity, shift the bonds, and you create new molecules. Let us zoom into two specific types: chain and position isomerism. In chain isomerism, the carbon skeleton itself changes. For instance, pentane is a straight 5-carbon chain, but 2-methylbutane is a branched version of the same formula. Their boiling points differ because branching reduces intermolecular forces. Position isomerism, on the other hand, keeps the skeleton the same but shifts the location of a functional group or a double bond. A classic example is propanediol and propanediol. Both have 3 carbons and an O group, but the hydroxyl sits on different carbons. This small shift changes reactivity, solubility, and even uses. So, when you see a problem in exams, look carefully: is the skeleton changing or is the functional group moving? That will tell you whether it is chain or position isomerism. Next, we move to functional group isomerism and metamerism. Functional group isomers share a formula but differ in the actual functional group. Take C3H6O. It can be propanol, which has an aldehyde group, or propanone, which has a ketone group. Same formula, but completely different reactivities. Aldehydes readily oxidize to acids, while ketones resist oxidation. Metamerism is a little different. It occurs when you have different alkyl chains attached to a polyvalent atom like oxygen, nitrogen, or sulfur. For example, C4H10O can be ethoxyethane or methoxypropane. Both are ethers, but the alkyl groups on either side of the oxygen differ. So functional group isomers actually switch the group itself, while metamers shuffle the side chains. On screen, you can see the table comparing them. Functional change means new chemistry, while metamerism is more of a chain rearrangement. Now let's step into the three-dimensional world with stereoisomerism. Here, the connectivity is identical, but the spatial arrangement differs. There are two main categories: geometrical and optical isomerism. Geometrical isomerism arises when rotation is restricted, usually around a double bond. For example, CIS-butene has both methyl groups on the same side of the double bond, while trans-butene has them on opposite sides. These isomers differ in polarity, stability, and even physical properties like boiling point. As you see in the diagram, CIS and trans look like siblings but behave like strangers. This shows us how crucial 3D structure is. Just like how rearranging furniture in a room changes its use, rearranging groups in space changes the entire molecular behavior. Here comes the advanced level, optical isomerism. Imagine your left hand and right hand. They are mirror images, yet you cannot superimpose one on the other. Molecules can behave the same way if they contain a carbon atom attached to 4 different groups. This carbon is called a chiral center. Such molecules exist as 2 enantiomers. One rotates plane polarized light clockwise, called dextro, and the other rotates it anticlockwise, called levo. A classic example is lactic acid or 2-hydroxypropanoic acid, which has 1 chiral carbon. The 2 mirror image forms may look the same but can behave very differently in biological systems. In fact, in many medicines, one enantiomer is active while the other can be inactive or even harmful. On screen, you can see the wedge-dash structures of the 2 enantiomers of lactic acid. Chirality is nature's favorite trick. From sugars to amino acids, life itself is chirin. So, let's bring everything together. Isomerism is the reason chemistry has such breathtaking diversity. Structural isomers differ in connectivity, while stereoisomers differ in 3-dimensional orientation. These small differences cause huge variations in properties, boiling points, reactivity, color, smell, or biological function. That is why isomerism is central to drug design, petrochemicals, flavors, and biomolecules. In exams, always remember the golden key. Check connectivity first, then check spatial arrangement. That way, you will never confuse a structural isomer with a stereoisomer. Think of isomerism as the identity card of a molecule, same formulae on paper, but unique character in reality. I hope today's session made you see how small changes in bonding or orientation can create entirely new worlds of chemistry. Until next class, keep exploring molecules like detectives and enjoy the adventure of organic chemistry.